Okay, hey, my name is Frederic. I'm a software engineer at CoreOS, and I'm here to talk about Alertmanager on its way to high availability. I work on upstream Prometheus and Alertmanager and Kubernetes and pretty much everything connecting the two worlds. And I'm Branch on GitHub. So Alertmanager on its way to high availability, what does that actually mean? What am I going to talk about? So I want to talk about from what happens from an alert firing from Prometheus to an actual notification being sent out, then the actual high availability contract between Prometheus and Alertmanager, so how we actually achieve high availability between the two systems, the actual implementation, and what kind of implication does that have on an operator operating Alertmanager in a highly available manner. Before I start talking about everything else, how does CoreOS fit in to working on these projects? This all fits into our product Tectonic, which is self-driving Kubernetes, and as part of that we want to have self-driving monitoring systems, so that's exactly why we want to be in this community, be active, drive innovation. So just to give a general overview for those who may have not worked with Alertmanager itself so far, Alertmanager is the component that receives alerts that are fired from a Prometheus instance, but technically it doesn't actually have to be Prometheus, it just has to speak the same protocol and behave in the same way as Prometheus does. What it then does is it groups all of those alerts into one notification, and it potentially deduplicates them so that when alerts are firing again and again, that we don't actually send out notifications more often than we want to. And then once it's done all of those things, it actually sends them out with your favorite provider. So PagerDuty, Slack, email, whatever you want, pretty much. And there's also a webhook integration if anything you want to use is not per default included, then you can build it yourself. And one of the features that are important about the talk today is silencing. So that means if you, for example, have a planned maintenance window where you know your database is going to be offline for, let's say, 8 hours, you can already, you can put that into Alertmanager and you won't be notified about that because it's an alert or a notification that you're aware is going to happen. So this is the general architecture overview of Prometheus and Alertmanager, and specifically today we want to be talking about how alerts are generated from Prometheus, which is partly through PromQL and alerting rules, and those then potentially result in an alert actually being fired against Alertmanager. And we want to see what that contract between Prometheus and Alertmanager looks like. So just as an example of how Alertmanager could work is Prometheus is constantly evaluating these alerting rules and sends out alerts or fires alerts against Alertmanager every rule interval. So that could be every 10 seconds. It actually evaluates these alerting rules and actually fires alerts against Alertmanager every 10 seconds. So that's basically the contract that Prometheus and Alertmanager have among themselves. And then when Alertmanager receives all of these alerts, as we can see here, then it actually takes all of these, and we've seen before there were multiple alerts on high latency. It says, okay, there are 3 high latency alerts, there are 10 high error rate alerts, and 2 cache server slow alerts. And depending on your infrastructure, you can group them to whatever your need is. And potentially, depending on how you structure your notifications, you can actually include all the individual alerts in your notification. So, shortly or compact, Alertmanager is the component that reliably sends you notifications. And if we're talking about reliability, we want to talk about high availability. And that's essentially what we're here to talk about. So just as an example, I want to talk through why this is important to do. So you start a project and you write microservice number 1, microservice number 2, microservice number 3. And as you start getting users, they have some kind of expectation that your service is running. You maybe even have an SLA once you have paying customers. So you want to start monitoring your application with Prometheus. And at this point, you're only scraping the metrics from your clients or your service with Prometheus, and that allows you to write alerting rules. So essentially what you then do is you hook up Prometheus to Alertmanager, and you actually get notified if anything goes wrong. Well, but if your product is successful, right, you start scaling out, and you want to be highly available with your service because you have some kind of an SLA. And then you start scaling up, but you realize you're scaling up all of your user-facing services and have them highly available, but not your monitoring system. So you add an additional Prometheus instance to monitor all of those targets again, so you're highly available with Prometheus. And then you also send all of those alerts that you've developed before with your initial Prometheus instance against Alertmanager. But here in this diagram, we can already see again, we have a single point of failure, which is Alertmanager in this case. So if Alertmanager goes down, we will not be receiving any notifications. And that's essentially our most crucial point at this point, right? We have alerts that are firing. We know that something is wrong. It's just not reaching us. So we add another Alertmanager instance. But because of the feature set that we saw earlier, we still have a problem at this point, because Alertmanager in itself is deduplicating these alerts. But now, since we have two instances, it actually sends out these alerts, the notifications twice. That's exactly what we don't want. So what we've come up with for Alertmanager is that we implemented a gossip protocol between Alertmanager instances. And I want to talk through what how this gossip protocol does work, and what kind of implications that has for you running it. But first of all, I want to say, why did we actually decouple Alertmanager from Prometheus? Well, it's exactly because of the complexity that we just saw, that we can keep all of this state sharing, gossiping, integrations with notification providers, that we can keep all of that separated in a separate component. And even that component could potentially be used by other monitoring systems. They just need to speak the same protocol that Prometheus sends against the Alertmanager. And yeah, that keeps everything simple in Prometheus from alerting side, so we only evaluate these rules, and everything else, complex distributed systems, can be done in the Alertmanager. So let's see what an example alerting rule would look like in Prometheus. So here I'm taking one of the metrics that are actually exposed by etcd, one of the CoreOS products or projects. And in etcd, a problem could arise if there's no leader in an etcd cluster. So we say our alert name is no leader, and this alert triggers if some time series does not have a leader at this moment, and if that stays for 10 minutes, then we fire this alert. And we can add some description what that actually means. We can template some things in there, but this is a very simple alerting rule how we would write it for Prometheus. And let's be clear that this is actually something that is evaluated in Prometheus, not in Alertmanager. But this does result in Prometheus constantly, or in repeat and rule evaluation interval, does actually send every 15 seconds, or however you have configured Prometheus to evaluate the rules, it actually sends these alerts every time it triggers. And that's very important for the high availability model between the two. So because we constantly send these alerts, how we can tell that an alert has been resolved is that if the resolve timeout has been reached, for example, if after 5 minutes our alerts are not firing anymore, we know that the problem has been fixed. And then this is an example configuration for the alert manager, which groups by the job, so that we can logically group all the alerts for, let's see, our etcd cluster. And then we can say that we always want to collect for 10 seconds all the alerts that are coming in, and then we want to send them out in a batch. And in this example, just because it's very simple, I use the webhook, but it could be any other integration that we have. So from a high-level perspective, this is what an alert goes through once it's reached the alert manager. So the very first step is the silencing, where we decide, do we actually want to continue going through this notification pipeline, or have we silenced this alert, thus we don't want to even consider sending it out. The next point is very crucial for the high availability mode. And if you're not running it in high availability, this is basically skipped. But depending on your position, on an alert manager instance position in the cluster, it waits for a certain period of time for the gossip data to come around from other instances and potentially deduplicate. Because the very next step is to deduplicate whether this notification has already been sent out. Then it actually sends out the notification, and then the important part where it actually sends the notification that a notification has been sent out to the other alert manager instances. And we will see why that is very important. I'll have a visual demo of that later. So what data is actually gossiped? The point that we just looked at, it's the send notifications. That data is gossip, but also the silences. So whenever we create the silence in Alert Manager, those are also communicated via the gossip protocol. What is not gossiped is the alerts that have been received by the firing system, because that's just the sheer amount of that would be too large to be able to gossip in larger setups, whereas notifications are a tiny fraction of the received alerts. And how did we achieve this? Well, we used CRDTs, so conflict-free replicated data types. So that means that we basically can merge all of these states without conflict, and we always end up with the same data, basically. And no, that's actually wrong. It's not well suited for CP systems, but it's well suited for AP systems in CAP theorem, because this is exactly what we want to achieve with high availability. We want to have an available and partition-tolerant system. And how did we implementation-wise do this? We used a library called Mesh by Weaveworks. And because we're using CRDTs here, or because Mesh requires us to have an eventually consistent model, that's what we have. So we have a last writer wins model, where timestamp based, basically whatever the latest timestamp is wins. Arguably, we could replace that with vector clocks, for example, but so far we haven't had any problems, so we're sticking with that for now. But it could definitely be exchanged. But yeah, basically we can just merge all of these things based on a unique ID. And it's quite important to know how these unique IDs are generated to be able to understand the availability model. But just looking back at why are we actually implementing a complex distributed system ourselves, and not use something like etcd. Well, etcd is actually not the kind of model that we want to achieve. etcd is CP, not AP. And the advantage would also be that the alert manager is actually single binary, so it's very easy to operate. And it's just less moving parts, because if we had a distributed data store that would be backing for our system, then that would be a lot harder to operate or even troubleshoot if there are any problems with it. So let's look at silences. We have two alert manager instances, and we want to perform create action on those, and want to see what that means in our gossip protocol. So the first thing that actually happens is some user actually creates or wants to create a silence through the HTTP API, for example. And what Alert Manager 0, because Alert Manager 0 received this request actually does, is it inserts it into its own in-memory database. And once it's done that, it basically takes the delta that was just inserted into its own database and gossips that to all other Alert Manager instances with the unique identifier, which for silences is just some randomly created unique ID. And then since Alert Manager 1 just gets that delta, it merges it into its data set, and eventually they all end up with the same data. So how would that work with updating a silence? Because let's say someone got sick and you are moving the maintenance window to next week, so you want to change the start and end date, or just the start date of a silence. So you just need to know the unique ID, which is in all of the databases of the Alert Manager instances, and say what you want to modify. And what then happens is that the Alert Manager 0 merges that into its own in-memory database, has the delta that has actually changed, gossips that to the other Alert Manager instances, and they merge that into their state, and we are actually consistent. So for the silences, that's an easier model than for notifications, because for silences, we can always just create a new unique ID. But for notifications, we need to be able to recreate the ID in a consistent manner. So let's just see how we want the Alert Manager to behave in certain cases. So in the first case, I want to show a case where there's actually no failure, but so like the happy case with a non-silenced alert, so that the alert actually gets sent out. So Prometheus evaluates some alerting rule and decides that it's going to be firing. So it fires them against both Alert Manager instances. And because Alert Manager 0 is positioned 0 in the cluster, it waits for 0 seconds, and Alert Manager 1 for 5 seconds. And so while Alert Manager 1 waits for the 5 seconds, Alert Manager 0 actually continues through the notification pipeline. So at first wants to deduplicate the alert, but it sees that there has actually not been a notification for this alert so far. So it actually sends them out with pager duty, for example. And then gossips the state that this notification has already been sent out. And once Alert Manager 1 has waited the 5 seconds, then it will, or while it has waited, it receives the gossip data, merged it into its state, and therefore, once it goes on to deduplicate, it does not actually send this notification out. So, but what does then happen when there's a network partition from one Alert Manager to the other, so that it was not able to gossip the notification that has been sent out? Well, because we were aiming to build an available system, we always want to say we at least once send out our notifications. So the terrible thing would be for the Alert Manager that it doesn't send out a notification, right? So in a failure case, we always make sure that at least one notification gets sent out. And so while Alertmanager 0 was trying to gossip its data, it failed because of the network partition. And then Alertmanager 1 was trying to duplicate, but actually sent it because it has not received the gossip data. And so we have a notion of at least once sending a notification. So how does that work? Let's say that we're actually able to generate this unique identifier for each of the notifications at the point where a Prometheus or a system that behaves like Prometheus fires an alert against the alert manager, 0 in this case. It, once it's sent out, adds the notification to its database. So things like, is it resolved? When was the last notification sent out? And it works very similar to the silences log, where it just takes the delta again and gossips that. So, but how do we actually get the unique identifier then? So what we do is, when we look at the actual route a alert goes through in the alert manager, we always say things like group by job, for example. So at runtime, we take the values of these labels and take all of those from all the alerts that are going to be in one notification. We hash them and then XOR them with the entire route that it's gone through, because the route can be a tree, so we need to go the entire route up. And then at the end, we actually concatenate that with the receiver, because a route can send it out to multiple receivers. So at that point, we then know that we've sent it out for that specific receiver, for that specific set of alerts in a notification. So now that I've shown how this is supposed to be working in theory, let's see that this actually works. So I've prepared a little demo. So, is that large enough? Okay. So I have a simple alert manager configuration here, very similar to the one that I showed in my presentation, except that I group by alert name here, and whether that's a good idea or not is another discussion, but just for the sake of this presentation, we have a group wait of 10 seconds, so we'll wait for 10 seconds to actually send out a notification, and within that time we group notifications. And we would send it out every 1 hour if these alerts keep firing, and we send it out with a webhook. And I've prepared a proc file here, how I'll run 3 alert manager instances, and an example webhook, which will listen on the address that I had in my configuration. And the webhook is really just a very simple Go application which just listens on HTTP on port 5001 and then just writes everything that it receives to standard out. So let's give that a spin. And everything's running, so let's go to the first Alert Manager web UI, which would be 1993. And we see that there are no silences created yet. So the first thing I want to show is that the gossiping of silences actually works. So we go through all of these Alert Manager instances and see, no, there has indeed not been a silence created so far. So we can take a random Alert Manager instance and just create something. So alert name equals high latency, for example. And I need to insert an email, and a comment could be something like, hi from KubeCon. And we create that, and we see down here that the alert has been, the silence has been created. And now we can check at all of our other instances. that this silence has indeed been gossiped to the other instances. So, now we've seen that silences creating works. So let's look at an example where there would be actually something firing against the alert manager. So we're simulating what Prometheus or a Prometheus-like system would do in this case. So I have a small script here called send alerts, which just sends a couple of alerts to my alert manager instances. And we'll have to be quick here because within 10 seconds, we should now see that the alert manager actually sends it out, and the webhook server printed it out to standard out. And what we want to see is that even though these alerts have been sent to all of the alert manager instances, only one of them has sent out the notification. And since the webhook server prints out everything it receives on standard out, we have only gotten one JSON blob, and that is exactly what we wanted to achieve. And that is basically the end of my demo, and that makes the end of my presentation. Just as a very last slide, we're also hiring in Berlin or all over the world at all our CoreOS offices. And if you have any questions, I'm happy to answer them now. Yes.
I was wondering, what's the advantage of using gossip protocol with delayed notifications over some form of leadership election, for example?
Okay, so the question was why didn't we choose something like in a form of a leadership? So what we wanted to achieve is that we don't have any master. We wanted to have a masterless system because we want any node to be able to go down at any point in time and the system to be still available. Because typically systems that have a leader election are typically CP systems. So Paxos or Raft, for example, they're CP systems, right? But we wanted to have an AP system in this case. Okay, if there are no other questions, then yeah.
Just to make sure, so there's no database in Alertmanager, it's all in memory, right?
So it's an in-memory database, but it gets snapshotted every snapshot interval that you want. But there's a time where if the last snapshot was done and within that time and like T0 and T1 and the alert manager crashes, it doesn't actually persist that to disk. So that can happen, but we are on track with that. We do want to implement some kind of a write-ahead log or something in that manner to be able to do things like that. Yes?
How much storage do you need, for example, 1,000 notifications?
So 1,000 notifications is like, it's essentially free. So we haven't actually extensively benchmarked storage, but like memory usage is very low because we don't actually persist anything of the alerts that are coming in, and that's the high traffic, right? We only gossip and store the notifications that we've sent out, and we also garbage collect those after some retention time. So even if you do scale up to, let's say, that you need 16 gigs of RAM, you can still tune the retention period to be so that you only use memory within that controllable range. Yes.
So if I scale the alert manager, does it mean that the new alert manager has no shared knowledge? All you use just setting the delta, so it will fire in the beginning?
Okay, so the question was, if I now scale up Alert Manager, will it have no data? Does send out all of the alerts? No, actually, when an Alert Manager joins the network, it gets all of the data from the other alert managers. And it also periodically they periodically share all of their state and merge it into each other. So that way we make sure that at least periodically we always have the same state. Yes.
It's a bit off topic, but do you plan to implement something small feature like to replace Ops Genius or Pager on duty, so it can be part of Alertmanager that I don't need to send, and we can manage the schedule inside Alertmanager?
So we don't currently have a plan for anything like that, but you can, using the webhook, you can basically implement whatever you want, right? I mean, you still need some kind of a notification mechanism, right? Like if you want to, like email is already implemented, and other than that, you'll probably have to write a webhook if you have some proprietary system, let's say. Yes.
Well, I wanted to speak to that question. So in general, in Alertmanager, we don't want to duplicate features like actual management of people, their on-call schedules, escalation policies. That's really more for systems like PagerDuty, OpsGP, and so on. It's just like kind of a separate concern for us. For Alertmanager, it's really just about the routing of alerts to certain notification mechanisms. Okay, thanks.
Okay, I think that's it then. Thank you.